Yeah, thanks very much. Great to be here. I appreciate the organizers inviting me. Um, so I'm going to talk about stuff. It's a bit old maybe, but it seemed the most suitable for the topic of this workshop. Um, and so I'm interested in the physics of Fermi surfaces. So what is a Fermi surface? It's something that happens in the context of metals. So okay, what is a metal? Um, of course, you can think of the simplest case, which is a non-interacting metal. So let's consider some system of fermions hopping on the lattice. Non-interacting fermions with some global charge conservation symmetry. Um, of course, you could also have fermions moving in the continuum as well, if you prefer. I will kind of go back and forth between the lattice and the continuum in this talk. But anyway, so because it's non-interacting Hamiltonian, you just diagonalize the Hamiltonian in the single particle in basis of the single particle states. And the ground state, if you have some non-zero charge density of fermions, the ground state will involve these like occupied single particle states. And the Fermi surface is the boundary between the occupied and unoccupied states. And so the Fermi surface is really where all the low energy excitations live. For example, I could add an electron near the Fermi surface or add a hole near the Fermi surface. So you can already see that a metal is like very non-trivial object from a point of view of quantum field theory, because if you think about the effective field theory that governs these low energy excitations, it has low energy excitations that live on this codimension 1 surface in momentum space. Normally, for a QFT, you would say all the low energy physics happens at k equals 0, but that's not true in these metals. You have this low energy codimension 1 surface in momentum space, so it's much more gapless than a normal QFT. Of course, in real life, we always have interactions, so we want to include interactions, and then the kind of famous way to do that is through this Fermi liquid theory. So let's start with our non-interacting electron Hamiltonian, and then you can write it in terms of the single particle occupation numbers in momentum space. And now you switch on interactions and what happens. And so what Landau said is that basically you just need to switch on this very special kind of interaction, which is diagonal in the single particle occupation numbers. And that's a very special kind of interaction. A general interaction would scatter particles from one momentum to a different momentum. So it wouldn't commute with the single particle occupation numbers. But this interaction term does commute. Okay, why is it enough to just switch on these interactions? I mean, Landau had some arguments. Maybe the more modern way to think of it in terms of renormalization group, you think of this as being an effective field theory. And then the other terms that you could add are like irrelevant in the sense of RG. Yeah, but again, the physics is nearly the same. All the low energy physics happens near the Fermi surface, and it's phrased in terms of these quasi-particles, which are the things which when you change the single occupation number, you add a quasi-particle. But Fermi liquid theory is not the whole story. I mean, for many materials, it seems to be the right description, but then there are other materials where it's not the right description. Famous example is this cuprates, which originally became famous because of high temperature superconductivity, but there's also stuff going on in these materials. So above the superconductor temperature, you have this regime that people call the strange metal, and there's various things which are strange about it. And we don't really know like what the physics of a strange metal is, but certainly it can't be described by Fermi liquid theory. Fermi liquid theory, so strange metals very clearly has this T-linear resistivity. Fermi liquid theory cannot predict that. So you need some new theory, but it's very hard. Presumably these systems are very like strongly coupled, like in contrast to Fermi liquid theory. And strongly coupled quantum field theories are very difficult to understand theoretically. But the thing I want to say is that even in the absence of any specific theory, I believe that this Fermi surface should be viewed as a very fundamental property of a metal. And the other important property of a Fermi surface is Leibniz theorem. So Leibniz theorem is a relationship between the volume enclosed by the Fermi surface and some microscopic data. So on the lattice, it's where you have lattice translation symmetry. It's related to the charge per unit cell. Or if you go to the continuum, there's a simple statement, which is just that it's equal to the UV microscopic charge density. And so, yeah, so the fact that metals exist at non-zero charge density is kind of a really basic property of a metal. And it's related to the fact that you have this Fermi surface And so the charge density is actually determined by the Fermi surface. Okay, but if I want to tell you that the Fermi surface is a very general property of a metal beyond just this Fermi liquid theory, I have to explain what is a Fermi surface. I mean, in Fermi liquid theory, it's very clear. It's where the quasi-particles live. But it's not so clear in a strongly interacting system where quasi-particles are not well defined what Fermi surface even should mean in general. So the proposal that we had is that we should define it in terms of the language of emergent symmetry. And that's a language that can apply even in strongly coupled systems. So hopefully it's clear what I mean by emergent symmetry. So at the UV of a microscopic scale, say on the lattice, you have some UV symmetry group. But then in terms of RG, you flow to some effective IR theory, which will govern the low energy physics, and that will have some symmetry, which I call GIR. And GIR could be much larger than GUV. So that's what I mean by emergent symmetry. And so let's consider an example of non-interacting electrons in one spatial dimension. And so the UV theory, you can just imagine that you have some single particle dispersion relation that you get by solving the non-interacting Hamiltonian. And to get a metal, you want to switch the charge density to non-zero, so then you'll have some occupied single particle states. And so again, there's a Fermi surface in this system, but in 1D, a Fermi surface is just kind of 2 points. So KL and KR here are the Fermi surface points. So that's the UV theory. But now we want to talk about the IR. Of course, there's a non-interacting system, you can solve the whole RG flow exactly. But basically the point is that since all the low energy excitations live near these Fermi points, KO and KR, you just linearize the dispersion relation about those points. And if you do that, you'll see that the system is basically equivalent now to a massless Dirac fermion. But notice that this Dirac fermion is at zero charge densities. So charge density is not invariant under an RG flow. So even though the UV was a non-zero charge density, the IR can be zero charge density. But there is still a manifestation of the fact that you started with a UV theory that has this non-zero charge density. And it's manifested in the emergent symmetry. So specifically in this massless Dirac fermion, we know it has this emergent symmetry U1 left times U1 right. Basically, the left moving charge and right moving charge is separately conserved, or if you like, the vector charge and the axial charge. And then this emergent symmetry also has this property that has this chiral anomaly. So if you apply a background electric field, the right moving charge will become non-conserved, and you have this kind of quantized anomaly equation. And similarly for the left moving charge with the opposite sign. The total charge, of course, is conserved still. And this is an example of something that we call a Hooft anomaly. So whenever you have a background field which kind of leads to non-conservation of charge, that's a Hooft anomaly. And of course, we know it's related to SPT phases in one higher dimension. So the point I want to make is that the fact that you have this emergent symmetry and anomaly is what tells you that this massless Dirac fermion can arise out of a UV theory of non-zero charge density. Even though the charge density is not reflected in VIR, it's not directly reflected by non-zero charge density in VIR, but it's reflected kind of indirectly through this emergent symmetry and anomaly. Yep.
Appearing anywhere that anomaly?
Whoops, sorry. It doesn't appear in the coefficient of the anomaly, but it appears in Luttinger's theorem. You can derive Luttinger's theorem as a consequence of this anomaly.
Derive what?
You can derive Luttinger's theorem as a consequence of this anomaly, and then Luttinger's theorem tells you the charge density is equal to KL minus KR, right? Which you can encode in terms of how the UV translation maps into this emergent symmetry.
Thank you.
But the anomaly coefficient itself doesn't depend on KL minus KR, so yeah, so it's not reflected there. And so there's a similar story in higher dimensions. So like say in Fermi liquid theory, you have this Fermi surface, and then if you think about this effective Hamiltonian that I wrote for Fermi liquid theory, it has a property that it conserves the charge at each point of a Fermi surface individually. So you actually have infinitely many conserved quantities. There's one conserved quantity for each point on the Fermi surface, and there's infinitely many points. So it's infinitely many conserved quantities, or another way to say it is the emergent symmetry group is infinite dimensional. it's an infinite dimensional Lie group. And if you try to be very precise about what the group is, it's this thing called the loop group, which is the group of smooth functions from the circle into U1. But it just reflects the fact that the charge at each point of the Fermi surface is conserved. And so it turns out this emergent symmetry group also has a Hooft anomaly, just as it, as we saw in 1D, the 1D case. In a minute, I'll try to give you like the precise anomaly equation, but there are some subtleties for that. Let me just give you first the kind of intuitive picture for why you know that there must be an anomaly. And it's basically the same story as in 1D. So if you play an electric field, the electrons move in momentum space in response to the electric field. And so you'll see that as a consequence of this, the charge at any point of a Fermi surface is not conserved anymore because it kind of charge flowing in from the interior of a Fermi surface now. So that's the manifestation of a Hooft anomaly. And so the proposal that we have is that you should just define a Fermi surface. Saying if you're in two spatial dimensions, you define that a system in two spatial dimensions has a Fermi surface if it has an emergent loop group symmetry with non-trivial Hooft anomaly. And that's a definition which, can be completely general. It doesn't need to know anything about Fermi liquid theory. It can apply even in non-Fermi liquids because it's a it's a non-perturbative state, and it can apply in like very strongly coupled systems too. So that's what we believe is the definition of a Fermi surface in general. Yeah.
So in this definition, if I have different anomalies for the loop group symmetry, would that correspond to different Fermi surfaces?
Well, okay. If you classify the anomalies for this loop group, they're basically Z classified. So the only way you can have different anomalies to change the anomaly coefficient.
So then physically, what would the anomaly coefficient mean in terms of what it's telling me about the Fermi surface?
It's hard for me to give the answer because it's actually very hard to find examples in the anomaly coefficient isn't just one. Generically, what seems to happen if you tried to create a Fermi surface with anomaly coefficient 2, say, is that the Fermi surface would actually split up into two Fermi surfaces, each of which have anomaly coefficient 1. So it's kind of a generic behavior. So it's kind of hard to, you have to fine tune the model to get like anomaly coefficient 2. But it's basically saying that like it's kind of the degeneracy of a Fermi surface. Like if you have two bands and they happen to have a Fermi surface that sit on top of each other, that would be like anomaly coefficient 2.
Okay, I see. So there's a bunch of like nested Fermi surfaces would have larger anomaly coefficient in general.
Well, if they sit on top of each
Yeah,
other, if they're separated, then you would actually kind of change the loop group. You would say that it's like rather than maps from a circle into U1, you would consider maps from like disjoint unions of circles or something, and then that would have an anomaly coefficient 1. But yeah.
Okay, thanks.
Is there a way to understand this as a bulk boundary correspondence in momentum space?
Yeah, I mean,
like the anomaly of the Fermi surface is because there's a bulk Fermi C that.
I think so. I mean, we definitely said that in the paper. I never quite understood exactly what it means, but yeah, roughly, I think that should be the right picture. Yes. Yeah, the anomaly which you can think of as being from inflow from a bulk will imply the gaplessness. Yeah.
Okay, thank you.
Yeah. So let me first explain like how do you extract the actual Fermi surface from this? I said that the definition of a Fermi surface is that you have this emergent loop group symmetry, but like Fermi surface is an actual surface in momentum space, right? So where does that arise? And the way it arises is in the map between the UV symmetry and the IR. So the UV symmetry, let's assume that we have global charge conservation, and I wrote R squared because I assume we have continuous translation symmetry. You could also do a similar argument for lattice translation symmetry. You can also talk about, because it's a Lie group, you can talk about infinitesimal generators. For this R squared is just, the X and Y momentum are the infinitesimal generators. For the IR symmetry group, the infinitesimal generators are smooth function from the circle into R. Now, the thing is that although the UV symmetry group and IR symmetry group can be different, they have to be related because the UV symmetries have to act in the IR. So formally what this is, it has to be group homomorphism from the UV into the IR. And specifically, that means that you have to map from these infinitesimal generators in the UV into the IR infinitesimal generators. So by looking at how Px and Py map into these infinitesimal generators, which are parameterized in this way, you get two functions, Kx and Ky, from the circle into R. And so you think of that as tracing out this surface in momentum space, and you identify that as the Fermi surface. So now I want to come back to this question of how we classify the anomalies of this loop group symmetry. And so it turns out that what we can invoke to understand it is actually a map from U1 anomalies in D spatial dimensions to LU1 anomalies in D-1 spatial dimensions. Remember, LU1 was this loop group, which is the symmetry of Fermi liquid theory. So I won't try to give the general argument for why this statement is true, but let me kind of illustrate it by an example. So for example, in D equals 1, we can consider a chiral free fermion. So that would be the action for a chiral free fermion. And now let's imagine that we take the spatial direction, compactify it, so now the system lives on a circle, and then we also take the limit where we send, so this V is kind of the velocity, group velocity of the chiral fermion. We take the limit where the velocity goes to 0. Then now basically you effectively have a zero-dimensional system, but with an LU1 symmetry, because when you send V to 0, the particle doesn't move around in space anymore. And because the spatial direction is compactified, you kind of think of it as being effectively now a zero-dimensional system. But it has its LU1 symmetry, because wherever the particle is on this compactified circle, it just stays there. So that's kind of saying that the charge at each point is conserved. So because this chiral fermion had an anomaly, a U1 anomaly, that will be manifested in the anomaly of this loop group symmetry. So that's one way to understand this correspondence. And so specifically for 2D Fermi liquids, we're interested in the anomaly of a LU1 symmetry in D equals 2. So that will descend from the anomaly of the U1 symmetry in D equals 3. And then the anomaly equation for that is like this, looks like this. So this is the same as the anomaly, for example, of a vial semi-metal in 3+1D. So it's kind of, we also call that the chiral anomaly, I guess. And so this will also describe an LU1 anomaly in D equals 2. But you sort of think of, so here there's like the indices vary over 4 dimensions, right? So for U1 symmetry, that would be saying that you have free spatial directions and 1 time direction. So these are the 4. That's why you have a 4-dimensional Levi-Civita symbol here. In Fermi liquid theory, you only have 2 spatial dimensions rather than 3, but you think of the Fermi surface itself as being the extra dimension. So one of these kind of quote-unquote space-time coordinates will correspond to where you are on the Fermi surface. So the Fermi surface is like the extra dimension. I want to emphasize, I only think about it being an extra dimension from a point of view of defining this anomaly equation. Like I don't think it's physically an extra dimension, but you can at least to define this anomaly equation, you treat it as though it were an extra dimension. Sorry? Oh, m is the anomaly coefficient, which is quantized to be an integer. And as I mentioned, usually it's just 1.
1? Like 2? Is there a case with the m equal 2 in the 2D Fermi liquid?
In 2D Fermi liquid, it's usually 1. As I mentioned to Sal, the case where it's if you have 2 bands and the Fermi surface sits on top of each other, then that would be m equals 2, but it's kind of fine-tuned because normally the Fermi surface would separate.
Yeah. Thanks.
So can one start out with a lattice model and derive this, or this anomaly, or?
Well, that's tricky because it's an anomaly of an emergent symmetry, right?
So I should take this as a definition of a Fermi surface? Is that what it means?
Yeah. Well, I mean, that's one way to say it. I mean, maybe you can go the other way. You can show that from this anomaly equation, you can derive properties that are consistent with what we already know about Fermi liquid theory. In terms of like, how do I derive this like from Fermi liquid theory? I mean, in principle, it's possible to do it if you have an effective field theory description of Fermi liquid theory, but that in itself is a bit challenging to to derive. Maybe from this, I mean, I know in this cojoint orbit formalism, they say that this is like some linearization of what they were doing. So maybe that's could be viewed as a derivation.
And the gauge field here is just a background vector, real electromagnetism that you couple to the electron.
It's a background gauge field for the LU1 symmetry. So it's a bit more general than that. Like a U1 gauge field would be a special case of that. But it's because you have an LU1 symmetry, there's more general things you can couple to.
Okay.
And I don't want to say that like that corresponds to something you can actually do on the lattice. The anomaly equation is more of a formal device, but it has consequences which have physical implications, even if you don't directly apply these gauge fields.
Thank you.
Oh, excuse me. Oh, so maybe I have a silly question. So, in higher dimension, is the emergent symmetry group still loop group, or maybe
well,
I
it's
could
some
represent-
generalization. Like it instead of because it's mapped from the circle into U1 because in 2D the Fermi surface is a circle.
yeah,
in higher dimensions, the Fermi surface is like a sphere or something. So then it would be mapped from it.
Oh, so it will be some kind of higher sphere group, right?
Yeah.
Oh,
right.
thank you very much.
Sorry, I'm a bit confused. I thought this big A was a U1 connection, but it was for 3 plus 1D.
Right, but then when you kind of map
Yeah.
to this LU1 theory, now you should reinterpret it as being a gauge field for the LU1 symmetry.
That's fine. But what I wanted to ask then is, do you know what the inflow theory would be? So the 3 plus 1D SPT action in terms of LU1 gauge fields?
I mean, you can write like a 5D Chern-Simons term, which has this anomaly on the boundary. But if you want a physical interpretation of that, I don't really have one because it's like.
Presumably, there's some 4D topological theory in terms of LU1 connections of some principal LU1 bundle.
By 4D, you mean like including that's a space-time dimension.
Yeah, space-time dimension.
Yeah, I mean, you can write such a theory. It's basically described by this 5D Chern-Simons term. Yeah, I mean, yeah, you can write that theory. The physical interpretation, I don't have, but yeah, formally it exists, sure.
Okay.
So just there's maybe a subtlety here which is a little confusing. So the right-hand side of this anomaly equation. So this anomaly equation tells you the non-conservation of charge, right? But the right-hand side is quadratic in the gauge field. But if you think about this picture where you apply an electric field to Fermi liquid theory, it's sort of obvious that the violation charge conservation should be linear in the electric field. So how is that consistent with having a quadratic term here? And the answer is that even in addition to the electric field, you have to think about the Fermi surface itself kind of corresponds to a gauge field already, even in the absence of electric field. So basically, even in the absence of any external fields, the Fermi surface intrinsically has a gauge curvature associated with it. And it's basically it's the gauge curvature in the theta I direction. So where I is space, and theta is the direction along the Fermi surface. So you can define this gauge curvature using in terms of the LU1 gauge field, and basically you want it to be determined by the Fermi wave vector. So K Fermi is basically the wave vector that it traces out the Fermi surface. So we kind of said that in the original papers we wrote. I don't think we had a clear physical picture of why, except that you need to do it to get the right answer. But I did like the argument in this paper, which they say there's kind of encodes the non-commutativity of position and momentum, because the theta is a coordinate on the Fermi surface, which is a momentum coordinate, and so momentum and position has to kind of not commute. So that's why you have to introduce this gauge curvature. But anyway, so then that kind of answers this question. So you have a term that's linear on the electric field, but then it also involves this intrinsic gauge curvature. So that explains why it's quadratic. And so a lot of things which you might have thought were just properties of Fermi liquid theory, actually you can derive directly from this anomaly, which means that they're true more generally. They would apply in any system that has this emergent symmetry anomaly, not just Fermi liquid theory. So Leibniz theorem, for example, is an example of that. You can derive that from the emergent symmetry anomaly. There's also things you can derive like quantum oscillations, the Drude weight. The fact that the Drude weight is generically non-zero in a metal. That's a consequence also of this emergent symmetry anomaly. So the point is that just from this emergent symmetry anomaly, which we believe will be true, even in non-Fermi liquids, you can derive a lot of the properties of metals. So in that sense, it's a very general argument. So in the time that I left, I don't know how much time I have left because there's many questions already, but yeah, I just want to mention one application, which is building this into holography. So the idea of holography is that if you have a quantum field theory in d space-time dimensions, it might be dual to a quantum gravity theory in d+1 space-time dimensions. So the interesting case for us is the case where the quantum gravity theory is weakly coupled, because then you basically just solve classical equations of motion, like Einstein equations for the metric, for example. And then this duality is kind of a weak strong duality. So the weakly coupled limit of the quantum gravity theory will be dual to a very strongly coupled quantum field theory. So this is a way to access the physics of strongly coupled quantum field theories via this duality to a weakly coupled system. And so you could ask, well, what is the point of this from the perspective of condensed matter? Well, firstly, if you want to apply this, you need to consider a QFT that has a weakly coupled holographic dual, because that's kind of the idea. Unless its quantum gravity field is weakly coupled, you won't be able to do anything. And so it seems that if you want a quantum field theory that's dual to a weakly coupled gravitational theory, it has to be in some kind of large n limit. In the real systems that we care about, maybe like strange metals or whatever, they're not going to be in some large n limit. Of course, in condensed matter, we often introduce like some parameter n and then do 1 over n expansion and stuff, and hope that we're capturing something about the physics even at n equals 1. But I think that maybe the better way to say what is the role of holography is that it's a way to think about general principles that govern strongly coupled quantum systems. And so a famous example of that is this like quantum chaos bound that's conjectured by Malder-Svinoshenko in Stanford. So they propose this bound on the Lyapunov exponent in terms of this kind of Planckian timescale. And so they conjecture that this is a bound that holds in any system, but specifically it's saturated in systems that have weakly coupled holographic duals. I don't know if that was their motivation for introducing this bound or not, but anyway, the point is that by thinking about holography, you're very naturally to think about this idea that there may be some universal behavior that involves this Planckian timescale, because that's what happens in these holographic models. And so the hope would be that this tin linear resistivity in strange metals also could be understood in this way. So there are these arguments about like maybe in these strange metals, like by analyzing the experimental data, it's been suggested that they have some like transport timescale that's also Planckian. So it's kind of hard to turn that into a general statement like this, because you would have to define what does this transport timescale mean in a general system, which is hard to do. But anyway, it does suggest that maybe there's a role of there could be a role of holographic models in terms of understanding where this Planckian timescale comes from. But then when you actually try to do that, you kind of run into difficulties. At least people have looked at this quite a bit in past work. And so the simplest thing to do is you take some CFT, which is supposed to be have a holographic dual. You switch on a non-zero charge density, and in the gravitational theory, that's constant switch on an electric field in the near boundary region. And so now you have to solve Einstein equations coupled to electromagnetism, and you basically find that there's a charged black hole. And that charged black hole is there even at zero temperature, at least in the simplest versions of this model. And so there's a lot of pathologies associated with that. You have this like local quantum criticality where the dynamical critical exponent is infinity. So this space doesn't scale under the RG flow. There's also non-zero entropy density. And these are probably not things you expect to happen in physically reasonable models of metals, for example. But the other worrying thing is that the Fermi surface, like there is some sense in which you can compute a Fermi surface in these models, but it's much smaller than it's supposed to be, according to Lunge's theorem, basically because the charge inside the black hole doesn't contribute to the Fermi surface. And again, that seems bad. Like metals should obey Lunge's theorem. And I mean, there are some variants of these models where you do also stuff like you introduce like extra dilaton fields. But certainly for me, I don't find any of them very satisfactory in terms of connecting to like reasonable phenomenology of metals that you would expect to see in condensed matter systems. So what is the way forward? And so the proposal was that, so the kind of previous attempts are basically trying to describe something like this UV theory. I mean, they start from CFTs, right? So it wouldn't be this like quadratic dispersion, it would be like a linear dispersion. And then obviously in holography, you're studying strongly coupled CFTs, not non-interacting CFTs. But basically, you're switching on its non-zero charge density and trying to find out what happens. So maybe instead of trying to do that, you should just look at this IR theory, which is actually a zero charge density, but it has a emergent this emergent symmetry. And so the idea is that rather than trying to find a holographic dual of these non-zero charge density theories, you try to find a holographic dual of these IR theories, which should flow from a UV theory and non-zero charge density, but you don't try to describe that holographically. You just try to describe this IR theory holographically. And basically, the point is that we just need to introduce emergent symmetry and make it have the appropriate anomaly. And so basically, you want to find a quantum field theory that has this global LU1 symmetry. I mean, in the holographic dictionary, that corresponds to dynamical gauge field in the bulk. And then you want that LU1 symmetry to have a Hooft anomaly. So you switch on a Chern-Simons term for that gauge field in the bulk. So the action ends up looking something like this. So you have an LU1 gauge field in your gravitational theory. And then you have a Maxwell term for that gauge field, and then you also have this Chern-Simons term, which implements the anomaly, and then the usual gravitational action. And so, okay, this theory turns out to be pretty easy to solve. And so, for example, I can compute the Green's function of the LU1 charge density. It looks basically reasonable. So the leading behavior is kind of the first term here. And so it has this pole at omega equals q perp, which describes like an undamped ballistic mode, so q perp is the momentum perpendicular to the Fermi surface. So basically it's telling you that you have a ballistic mode that moves radially to the Fermi surface, which is what you would expect in Fermi liquid theory, for example. But you see it also in this holographic model. So it's kind of nice to have this correspondence. Like you get reasonable behavior, more or less reasonable behavior from a metal, at least in terms of this Green's function. You also have this non-Fermi liquid correction. So I don't think we're actually describing Fermi liquid theory. It's just that like this first term, it probably comes just from the LU1 symmetry. It doesn't really need quasi-particles or anything. But I think the really interesting stuff would be to switch on dissipation. But to do that, you actually have to break the LU1 symmetry, because, like, for example, in Fermi liquid theory, the leading contribution to resistivity comes from these like Umklapp scattering terms, which actually break LU1 symmetry. You could say that they're irrelevant because, yeah, I mean, they're irrelevant under RG probably, but so there's an emergent symmetry, but they're dangerously irrelevant because they determine the leading behavior of resistivity. So really, I think the next step is to switch on terms like this in the holographic models. And then I hope that we'll get really interesting behavior, but I'm still working on how exactly best way to do this is. Okay, so to conclude, what I argued is that a general non-perturbative way to define Fermi surface is through this infinite dimensional emergent symmetry group and its anomaly. And so you could ask the question, I mean, I believe the answer to this question is yes, but I can't prove that rigorously. Does every metal have this emergent symmetry structure, even if it's like some strongly coupled non-Fermi liquid? So I think the answer should be yes, but yeah, it would be interesting to test that statement. And then also, I would like to understand more about holographic models of metals that build this structure in. All right, thank you.
I have a very naive questions. If the Fermi surface has the bed curvature, enclosed bed curvature, how does the anomaly equation change?
Well, the anomaly equation
remains the same.
This Berry curvature, I think the right way to think about it in this formalism is actually a component of the LU1 gauge field.
Yeah.
So it enters into the anomaly equation is what it is, but like if you switch on this Berry curvature, you switch on a component of the A, and so that will appear in the anomaly equation.
Okay, thanks.
So in holographic models, sometimes these symmetries can be extended to some kind of geometric construction with more dimensions apart from the D+1 that you have. So have you thought about this kind of thing?
No, I haven't thought about that. I mean, I just assumed that we have this loop group symmetry. In terms of like where that would arise from, like some string theory, that I definitely haven't thought about. I think that's maybe the context where you would get what you're describing.
Okay, thanks.
A very naive question. So in this there's gravitation, if I understand correctly, in this holographic model.
Sorry, I think I missed the question.
Sorry. So can you go back a few slides?
Yeah, this one. Maybe.
Yeah, exactly. S graph. So this is like a Einstein gravity, or
Einstein gravity.
yeah,
with cosmological constant. That's the usual.
exactly. That is the question. So what is this? Is it the negative cosmological? So is it the ADS basically, or?
Yeah, it's the same. It's just the same as it would be in the usual ADS CFT. So yeah, negative. Yeah.
And is there a chance to turn off the cosmological constant?
Well, I mean, that's a very difficult question, right?
Yeah.
I mean, that's
of course. Yeah.
yeah. I mean, I'm not an expert in holography, but I know people trying to study like flat holography. But yeah, I don't know anything about that.
Thank you.
For dissipation, can you consider a black hole configuration?
Well, yeah. I mean, the model as written doesn't have any. Well, actually, I guess at non-zero temperature it would have a black hole, but that black hole doesn't contribute to the electrical resistivity. You know, I mean, it gives you other kinds of dissipation, but for electrical resistivity, I mean, you need to introduce this LU1 symmetry breaking, and then that will presumably couple to the black hole in some way and give you the resistivity. So, I mean, dissipation in holography always comes from a black hole, but exactly how that will work once you introduce LU1 symmetry breaking terms, I'm not sure yet.
Oh, so the symmetry here we're talking about is the zero form symmetry, isn't it?
It's a zero form symmetry, yes.
So what about generalized to the higher form symmetry? Do we still have some, for example, matching pattern between the UV and IR theory that we can investigate to have the same picture?
You mean if you place like the microscopic global U1 zero form symmetry for one form symmetry?
Yes.
Yeah, sure. I mean, you can definitely do that. I mean, I think these like Rodinger theorems and stuff will have a generalization to that case. I don't remember exactly what it looks like, but like, yeah, I mean, I think also if you have like some generic charge density of the U1 symmetry, that is reflected in some anomaly in the IR. Like, I think that's what happens in like Maxwell electromagnetism. Like the Maxwell electromagnetism, you can have Maxwell electromagnetism in 3+1D has some, you know, 2 one-form symmetries, and you can have an arbitrary charge density of like each of them, and that's reflected in the fact that you have this like in the IR you have the 2 one-form symmetries and they have mixed anomaly.
Yeah. Okay. Thank you.
Hi. Just one question. If we consider the spontaneous symmetry breaking of this LU1 global symmetry in the Fermi surface, should we expect, for example, like infinite types of Goldstone's mode?
Yeah, there would be, but I don't know if that ever physically happens. Like in a superconductor, I think what happens is that only the U1 gets spontaneously broken. The LU1, the rest of the LU1 doesn't get broken. So in terms of like a system, when could you have a system that actually spontaneously breaks the whole LU1? Yeah, I don't know if that can happen, but it would be interesting to think about.
I see. Thank you.
Actually, a follow-up to that question. Do you know what happens if you have some Pomeranchuk instabilities? Is that some symmetry breaking of the LU1?
Well, Pomeranchuk instability just I mean, on either, it just like the resulting state is a new Fermi liquid. It's just that its Fermi surface gets kind of shifted, like breaking some symmetry. So on either side of the transition, it'll just be Fermi liquid, very described by this story. At the critical point, that's a non-Fermi liquid now, like it's a non-Fermi liquid, but I believe that it's still described by this LU1. I mean, yeah.
Okay, thanks.
Okay, so if there's no more questions left.
Yeah, so it seems like this extra dimension, the parameter theta that you have, this is a coordinate that describe where you are in the Fermi surface. But wouldn't it weird that effective theory also contains like both coordinate in the real space and in the momentum space at the same time? Like, I mean, how would one do the gradient expansion in this story if we were to use this LU1 symmetry?
I mean, maybe it's helpful to think of it as I mean, there's some separation of scales, right? Like this momentum space, Fermi surface lives are approximately kf, whereas like, you know, the physics you care about will be some very long wavelength thing. So it's kind of some separation between like the small gradient, long wavelength fluctuations, which you would appear in some gradient expansion, and then this kf is kind of, you could at those timescales you can almost think of this k as being just like an internal coordinate now. It's just it's an internal coordinate that has like infinitely many values.
Okay, thank you.
That's not